Yeah. Right?
What?
I'm in the class now, right? Yeah.
I don't want to make any promises.
Even the city doesn't understand. You said yeah. You called my name. I know. I didn't want
to. No. Well, I'll talk to administration. No, I didn't tell you were enrolled. You could try. Remember? You're encouraged to come to the first day, but like almost everyone's here that's enrolled, unfortunately. I'm sorry. Yeah. It made you feel better. I was always on like the wait list for my major classes. It was really hard to get in the first few years, yeah. Especially you don't have priority. Yeah. But I'll try my best. Okay, but I don't want to get your hopes up.
I just in summer can be, so I better be in this class.
I mean, there's spots at Yuba.
But I like
No, I appreciate that. No, I'm just telling you the facts. All right, everyone. It's about 10 minutes, so let's start talking about Chem. Okay, what is organic chemistry? All right, so I hope this works. All right, so organic chemistry. So at any point, if you need me to slow down or if you need me to clarify what I just wrote, let me know. I don't have the nicest handwriting, but I think it's okay. Okay. So organic chemistry. What is organic chemistry? So I always like to start by a little history of OChem. Okay. So on Earth, right? What compound do all living things have on our Earth? Or what element? Carbon. Thank you. All living things are made up of carbon compounds. All right? So the Earth is considered non-living. It's made up of mostly sand or silicon. But us, living things that populate the Earth, we are actually made up of the element directly above the Earth's main element, carbon here, right? Okay, so silicon and carbon have a lot of similarities, but it just turns out living systems is based on the carbon and not silicon, okay? So I like to think of organic chemistry, people may debate me for this, is the chemistry of life, because it deals with the chemistry of carbon. Okay. Then it's interesting to think like what about the temperature of Mars, our planet, is it based on carbon? Because a lot of things on Mars, it doesn't directly correlate with things on Earth, so it makes for interesting conversations, especially amongst people who enjoy space. Okay, so a big thing about organic chemistry, it was once believed that you can't make carbon compounds from non-living things. It was thought, like in the 1800s, it was thought there was this concept called vitalism, which basically meant living things can only, or living compounds from a living thing can only be made from living things themselves, right? But we soon realized that that's not possible. Challenge accepted, okay? We can make compounds from non-living things that have carbon in it, okay? So what I want to point out here is that a key component is that compounds can be made from non-living materials. Okay, so the German chemist, so a little bit of history, a little bit of perspective here. German chemist, Friedrich. All right, if anyone's German, I sorry about my German, okay? Rohr, probably wrong. Okay, so he was the first one to synthesize urea. In the 1800s, the 19th century here. And we know urea, right? Where's urea commonly found? It's a bodily fluid, right? It's a waste excrement when you go to the bathroom, right? But urea is primarily formed in the body, so it's kind of odd. At the time, people didn't think you could make urea from, say, fertilizer or something you got from the ground. So it wasn't a popular opinion at the time. But this discovery here kind of paved the way for like, oh, organic chemistry can be like art. We can create any organic compound from from a substance or a compound that's not usually found in living things or not from a living thing. Okay? All right. So organic chemistry used today, we find it in many aspects of our life. Right? So, let's talk about the compounds today. What's one compound, or what's one class of, like kind of a material or maybe a product that you think comes from chemistry? So, let's see. I'll start us off. So, many of these compounds are part of the list of products I'm going to write. So, they're found in plastics. Does anyone have another idea where we might find organic compounds in society or maybe in your everyday life? Fuel, good. Great, okay. So we use soaps, right? Soaps are from animal and plant fat. Well, mainly vegetable oils and fat. We have soaps. Foods, right? Spray deodorant on or like perfumes. Those have chemicals too. Yes. Polyesters. Good. And where do we usually find polyesters in? What kind of material? Clothing, right? Clothing. Good. You're right. Exactly. Clothing, polyesters, many like polyamides, polycarbonates. Those are usually found in products that you can't normally just produce using one chemical. You have to, it's a whole process. Very good. So we have clothing, perfumes, even sweeteners. Like sugar-free gum, that's not from like table sugar. It's from a different compound, a artificial substance that looks like table sugar, but it gives you a sweeter profile when you eat it. All right, so clothing falls under fabrics. So I'll just list fabrics here too. All right, can you guys see that? Are you guys okay in the back there? Can you see that? Is that okay? You need me to zoom in? There we go. All right. All right, and then a big industry today is towards medicine, right? Pharmaceuticals, which is a very complicated business model. Well, pharmaceuticals, the way they do it is the main reason I actually don't even try to go work at a pharmaceutical company. Just seems a bit immoral to me. But companies like this are like places as a chemist you can go work. I just enjoy teaching a little bit more. Okay, and then there's many others of these in daily life. Okay, and many others. So these are just a small fraction of compounds here. Okay, are there any questions so far? No? All right. So that's our little introduction here. Now let's talk, we're going to do kind of a brief course here on review of the atom and basically the skills you need, you should have learned before coming to this class, okay? Just a brief overview of chemistry in general. All right, so I did try recording this, so hopefully it records. I'll find out after today. But I've done recordings before, just like mirroring or in a screen record, so they should work out fine, I think. All right, so I'll just scoot this up a little bit. All right, so let's draw a line here. All right, so I like to use different color pens just so it's not boring. Okay. Atomic structure. Okay, so the structure of the atom, in simplistic terms, we have a circle, okay? All right, we have two positions here. What's at the center of the atom? Yeah, the nucleus. Right, at the nucleus, this is where our protons and neutrons are. If you go study physics, you might unveil what protons and neutrons are made of, but that's not the point here. All right, so this area here is kind of vague. What's this area around that dot? Yes, good. So I'm just going to be very vague here. This space around here, space here, is the electron cloud. So, you might have noticed in chemistry, we can't actually put a boundary on the atom because the electrons are what we say quantum objects. They're so small, you can't pinpoint where they are at any moment. You can only guess or suggest a probability of where it could be, right? So that's why there's this line here. I don't specify that, the electrons are exactly at this little circle. You can't say that, okay? So the quantum realm of electrons is very different from an object where something is physically there and occupies space. But we already covered that in 1B or 1A, so we don't need to worry too much about that anymore. I just want you to realize the electrons are here, and at the center are the nucleus, where we have the more massive protons and neutrons. Okay? So this is where the electrons are, I'm just going to put found in parentheses, because in reality, you can't say they are found at that region. You can just say there's a good probability. Okay? It's something we have to kind of just accept as a limitation to our understanding. Okay, are there any general questions about the atomic structure? I don't want to go too deeply into that because this is not a Gen Chem. No? Okay, so stuff we've seen before. All right. So, we must briefly go over electron configurations. All right. So for electron configurations, I just want you to know generally what they are. Okay, so for example, hydrogen. What's this configuration? Yeah, 1s1, right? So there's only a few atoms we have to worry about in this class because it's organic. Hydrogen, the second row elements, phosphorus, and chlorine. And that's pretty much it, and sulfur. Okay, so we're pretty much ignoring most of these. We don't care about these. Okay, unless you go to research, you won't even know what these are. And we don't really care about any of these, really. Okay, we're mostly focused on this top of the periodic table. So this subsection here, and a few transition metals, and some of these alkaline and alkaline earth metals. Okay, so you'll see me putting those in reactions or mentioning them, and that's because they have roles in chemistry since the history of it. Okay. Now, of course, there's some elements in there that are involved in organic chemistry, but that's a very advanced topic where you usually don't see that unless you go to grad school. Okay, so I will not mention most of those elements on the periodic table. All right, so that's why I say we should only worry about row 2 elements. So row 2, we have, all right. So to specify element in row 2, we can use helium as the noble gas shortcut. And then it usually has a configuration 2s, some number x, 2, sorry, let me just go back a bit. 2p, okay? So for example, if I specify carbon, what would those letters be? Helium, all right, carbon, second row, right? The S block is it filled? We look at carbon, right? So we have 2 electrons in the p orbital, and then how many in the s? 2. So for carbon, what would it be? Yeah, thank you. So carbon would be helium 2s2, 2p2. So the reason I write it this way is because you can see here, if we know the electron configuration, we can figure out how many valence electrons they have. And valence electrons are important because we're talking about reactions. So electrons are going to be transferred or shared, and you form new bonds, right? So if I look at carbon, you look at the valence shell, right? The valence shell is, whoops, I didn't mean that. So we look at these, right? Is this the valence shell or the core shell? Valence, right? Well, the valence is the outermost shell, right? So the highest energy level. So if I were to count how many valence electron carbon has, how many does it have? Good. Okay, so that's the proper way to determine valence electrons. But if you recall 1A, how did you determine an atom's valence electrons? By just looking at the periodic table. Let's just review that. The group number. All right, which group number? This one or the old one? Yeah, okay. So it's usually these ones with the Roman numerals here. So this says 7A, 6A, 5A. Oh, the carbon has 4 valence electrons, right? 4A. So that's why you look at the group number. That's a trick we'll have to use, okay? So if you're having trouble drawing Lewis structures, we'll need to practice that because we're going to draw them and pretty much not allude to how we got the structure. We're just going to have to know how to draw them by heart, okay? All right. So, for anything in the group 3, row 3, right, we have transition metals. So I will say sulfur. So we have sulfur, phosphorus, chlorine, and transition metals. Okay, they have electrons in d orbitals. Or, they have electrons in d orbitals, or d orbitals are available, okay? Or available. Okay, these orbitals are available. That means we can have expanded octets. Okay, what does this mean? More than 4 bonds / 8 electrons around central atom. All right, so we can't forget that. So some compounds, you'll see this in most notably is phosphates. And phosphates are part of DNA and RNA, right? So they are important for living organisms. So they're present in DNA, present everywhere. So usually you can test for life in like water and stuff. If there's phosphate in there, there's usually if you have a source of phosphate, that's usually mean there's like algae or fungus or anything living in water systems. Okay, so that's all I want to talk about electron configurations. The takeaway is just basically know how to write an electron configuration, so you can know its valence electrons. But if you remember the shortcut, use the periodic table as your guide, okay? On exams, you always get a periodic table, okay? So always use that as a resource. Okay. Any questions about configurations? No? All right. All right, so I like to highlight here just so it's a little bit organized. Excuse me. All right, now let's talk about the 2 most common forms of bonding in terms of organic chemistry. All right, so we're going to talk about chemical bonding now. Chemical All right, can someone tell me what's one of the 2 forms of chemical bonds here that you learned? When you're drawing like Lewis structures or Lewis symbols, what kind of bonding did you learn about? Yes.
Double bonding.
All right, I heard double bond, single bond. So what type of bonding is that? What kind of classification? Is it ionic or is it covalent? Covalent, right? So we talk about molecules, and so molecules will refer to covalent bonds, and then formula units or ionic compounds like metals or salts, those are ionic bonds, okay? So let's first talk about ionic bonding. Okay, so ionic bonding, a characteristic of ionic bonding is, are you composed of molecules in ionic bonding? Or what are you made of? What is found in an ionic compound? No, non-metal, right. And are they neutral, or or something special about them? They have charges, okay? So you have ions of opposite or opposing charge. So this is the electrostatic force. That's one of the forces that governs our existence in terms of physics. Opposite charges attract, right? just like gravity. It's kind of like gravity. Okay. So, and I heard it usually includes false bonding between a metal atom and non-metal. Very good. So, some examples. The obvious example is sodium what? Chloride. So sodium chloride is actually composed of sodium ions and chloride ions, right? So they're attracted by opposite charges attract, right? We know that. Okay? And then the other type one you'll see here in this class is not just a just a single positive charge. You might see stuff from double charges, so like magnesium chloride. In this case, what's the charge on magnesium? Thank you, good. Cl minus. You actually have two Cl minuses here, so there'll be actually two of them around the magnesium, okay? All right, and then I heard the other type of bonding, covalent. What's the difference here? Yeah, so do we form any ions? No, right? No ions are formed. You're just sharing electrons instead. So the reason why ions formed here is because, sodium here, right? Sodium 0 is giving its electron to chlorine 0, and this is becoming Na+, and this is becoming, so here, 1 electron here, Cl minus, right? That's how that works, okay? But for covalent bonding, what happens here is that two atoms share electrons to form a bond. And this is usually between what kind of atoms? Metals, non-metals, or one of each?
Non-metal.
Yep. So this is between two non-metal atoms. All right. We'll stop here today as our stopping point, and we'll pick up here and we'll talk about Lewis structures next time, okay? All right. If there's any general questions, please come talk to me after class. If there's nothing else, see you guys on Thursday.